Hello everyone, today we'll talk about the solution of the problem minimum cost to make at least one valid path in grid. As you can see, the statement is very long, the problem is classified as hard, so you might think that this is indeed a hard problem. But really once you read and understand the statement, you see that this is actually quite a standard problem, and you probably know how to solve it if you have some experience with grid problems or graph problems in general. We want to, as usual, get from the upper left corner to the lower right corner, or from 0, 0 to the highest coordinates that exist on this rectangular grid. And now, while the problem is framed as us being able to change the sign on any cell that we want with some cost, and the sign is an arrow pointing from the cell to one neighbor, meaning that we can go there from one cell to the other. And so it might seem like there are some difficulties in getting from one position to another position, that by changing the signs we change which positions are reachable. And of course it's indeed true, but it's much easier to think about situations like this, and this is a very common trick in problems like this, that this changing of a sign is equivalent to us just saying that if the sign is already what we want, we can traverse it, so go through the edge, let's say, so go from our cell to the neighboring cell according to the arrow for free, for our cost 0. And if the sign is wrong, then we can go from our cell to the neighboring cell with a cost of 1. And that corresponds to us changing the sign of a cell. By the way, we are being told that we can only do it once per cell, but it doesn't matter. We never want to change it more than once per cell, because in particular we never want to visit the same cell more than once. It's easy to see that since we want to have at least one valid path, and we visit the same cell twice, that means that we can essentially go through the path until we visit the cell for the first time, and now skip everything that's left in the path until we would have reached the cell another time, and in a way teleport to that position in time, and continue with the rest of the path. And the path is still correct, because we still just, both the situations were at the same cell, so you can just continue as if we skipped that portion of the path. So it doesn't really matter, we never want to modify the sign more than once. So in other words, we have some neighboring cells for which the cost is 3, and some for which the cost is 1. So you can use any technique that we want. We can use a so-called 0-1 BFS, but we can also just use our favorite Dijkstra's algorithm, and this is what I'm going to do here. This is the solution using the Dijkstra's algorithm. So first some boilerplate. We take the height and width of our grid, because it's going to be useful later when boundary checking. And we want to, of course, have our directions up, down, left, right. So those are the changes in row, changes in column. We zip them together, turn it into a couple, and we'll be iterating over this tuple of directions to go through all the directions. Now here the directions are in the order of 1, 2, 3, 4 from the task statement. And we'll be maintaining now for our Dijkstra the set of visited nodes and a priority queue of distance and row and column. While we still have something on our queue, we take the thing for which the distance is the smallest. If we've already visited it, calculated it, we don't do anything. If now we've reached the final position, this is the result, so we return the cost. Otherwise, we know that this is the cost for this position, so we add it to the visited. And now we go through all the neighbors. So we go through everything in differences, so the difference in row, difference in column, and differences. And this is the new row, new column. Of course, if it's out of bounds, we continue. And now we also want to enumerate this list of directions, starting from 1, so that D is the index for which the arrow would be correct. So if D is 2, that means this is the direction, since we enumerate from 1, the second direction in our array, so it's 0, minus 1. Indeed, 0, minus 1. And we do it because what is the cost of getting from RC to NR/NC? Well, the cost is the same as the cost for getting to RC, so our V, which we've got here from the queue. And we have to pay 1 if the direction is different than the direction written on the grid. We push it into the queue and that's it. We are guaranteed to be able to reach the final position, so we don't have to write anything after this while. Just at some point we're going to return from line 14, and that's the whole solution.